So this is going to be one of the shortest videos, just a little bit to talk about protein folding. So as we talk about protein folding, I want to highlight a couple of things. I want you to remember and envision me with my yellow pipe cleaner that takes that primary sequence and then wraps it around my finger to make coils that are going to be our alpha helices, that zigs and zags it back and forth to make our beta strands, which will interact to form beta sheets. And then once we have those secondary structural elements, what we are going to have is what's called hydrophobic collapse. Okay, and again, we see this theme here. Protein folding is driven by the hydrophobic effect, because if all we have is secondary structure in protein, technically it's unfolded. We don't really have structure until we have that tertiary structure that's driven by side chains, and particularly those hydrophobic side chains that want to minimize their contact with water. And so they're going to kind of clump together in the center of a protein, and then everything else is going to sort of nestle into place after that. Right? We talked about proteins like insulin, right? And the structure of insulin needs to be driven into that correct conformation by that C peptide that's going to sort of direct the formation of those correct disulfide bonds. Remember, disulfide bonds, they don't provide stability to structure as much as they help direct who should be next to who. So lots that we've already talked about in terms of protein folding, but I want to introduce a new concept here, which is the timing of how we think about folding, and in addition to that, the energetics. So I'm going to go through over here. We've got what we refer to as a folding funnel. And what I want you to envision with this is we've looked at reaction coordinates to think about the energetics of things, right? We've got time along our x-axis, and we've got energy along our y-axis. And we can think about it, if you were to imagine a protein folding, it sort of starts in a high energy state because we don't have a lot of interactions. You can think about this the other way, that if we wanted to unfold a protein and have no sort of intermolecular forces, we'd have to add energy in to get it up to there. So when we fold a protein, when we are making interactions and intermolecular forces, that's stabilizing. That's a really important concept to think about, that if we wanted to unfold a protein, we're going to need to put energy in, and that means our unfolded protein is going to be at a much higher energy state than a folded protein. So we could sort of envision that along a two-dimensional sort of situation where we've got a reaction coordinate, right? A folding funnel, I want you to think about, is really that mapped onto a three-dimensional space. So I want you to envision a funnel, right? And a funnel ultimately gets down to a narrow space at the bottom. The top of the folding funnel is going to be high energy. Okay, and that's where we're going to have our unfolded proteins. And as our protein begins to fold, forms intermolecular forces, that becomes stabilizing. And as we continue to form secondary structure and then tertiary structure, we get lower and lower in energy until we're finally sort of at our folded state. So I'm going to kind of zoom in here down to the bottom just to highlight and introduce a couple of terms. Right down here at this bottom piece here, I'm going to have a structure of the protein that is what we call native. Native meaning it's folded and then functional. Okay, and what we can see here for this folded and functional protein is we are going to have this beta strand sort of up here, and then we've got this one working in sort of the opposite direction, and then here we've got our green beta strand there. So we've got a beta sheet here that's formed from these secondary structural elements sort of all interacting. Well, what if these don't interact in sort of the correct way? And it's a little bit hard to see here, but here we've got this loop domain sort of in front of this beta strand here. So this is still folded, but it is misfolded. So this is misfolded. So it's still folded, okay? But it's now malfunctioning or malfunctional. Okay, so it's not folded into the correct three-dimensional shape, and so it's not functional. What we call this is a trap, because what's kind of happened here is we've had a lot of intermolecular forces that have formed and created a stable state, but unfortunately they sort of got off path early on, and they created this low energy species that is not folded correctly, and we call it trapped. So you can see here as we sort of come along this funnel, again, all of these structures that are up here are high energy. They're largely unfolded, don't have a lot of structure to them, no secondary structural elements that we have here. And again, as we begin forming our secondary structural elements. We become lower in energy, okay? And then we begin collapsing that hydrophobic domain and we get lower in energy. And the hope is that you eventually drop down into the correct low energy spot of your funnel, which is native, so folded and functional. I envision sort of like a Plinko game. I don't know if you remember Plinko, where you're basically dropping a ball and it's sort of like trying to get down into the right sort of funnel down in the bottom. And unfortunately, you can get off pathway here and then get trapped into this low energy space that might be hard to get out of. A lot of this is going to play into some of the misfolding protein diseases that we'll talk about in a subsequent video. So I kind of wanted to introduce you to this concept of sort of a three-dimensional energy landscape that is the folding funnel that we think about for protein folding. Now, I told you I was going to talk about sort of the time piece here. And even though we talked about protein folding is driven by the hydrophobic effect, here's the piece here that implies time. It's not a random walk. We've spent some time in this learning unit sort of talking about 100 mers. So whether it was a 100 mer piece of DNA that we don't have enough atoms to sort of build it because they'd be heavier than the weight of the earth, or we can't form all possibilities of a 100 mer protein because we don't even have enough atoms in the universe. Go watch the By the Numbers video if you need to remember what I'm talking about there. But I want to talk about a 100 mer protein. And I want to think about the fact that nature does not have enough time to evaluate every single possible conformation. It's not a random walk where it's kind of like looking for all possible conformations for that peptide backbone. And the reason is if that 100 mer were to sample every possible conformation, it would take 10 to the 87th seconds to sample all possible space. I'm going to kind of come down here because I ran out of room here. 10 to the 87th seconds to sample all conformations. And that isn't even possible because 10 to the 87th seconds is 20 billion years. That's 4 to 5 times the age of the universe. So we don't even have enough time to sample all possible conformations. So the point is it's not a random walk. It doesn't sample all possibilities. It basically is following sort of a folding path or pattern. So again, highlighting some of the rest of the words that we have here, right? Structure formation is entropically unfavorable, but that enthalpic compensation is what allows us to get lower in energy. But the challenges that we see here is that we have these thermodynamic traps in this folding funnel, right? This is a low energy species, but it's gone kind of down the wrong path, gone down a rabbit hole that it wasn't supposed to. And this is especially problematic when we think about folding proteins co-translationally as they're being synthesized by the ribosome. But I hope I've given you a couple of examples with insulin, and we're going to talk about a couple of other proteins that have to do with thinking about misfolding as they relate to disease in a subsequent video.